So indistinguishability obfuscation is a recent development in the theory of obfuscation. But before we get into that, let's just all recall, why we're here, right? So the big question here is an analog of the following question. Suppose that you want to keep a secret, right? But unfortunately for you, there's an adversary that has captured your entire brain, right, taken it out of your head and holds it in his hand, and in fact reads and tampers with every single neuron in your brain while you are thinking about the secret that you want to keep from the adversary. Right? This is a terrible, terrible situation. I hope none of you ever experienced this situation. I haven't heard of this happening to human beings yet, right? But on the other hand, we know this happens all the time to computer programs, right? The computer science analog of this is extremely common. Programs are routinely captured by adversaries. In fact, sometimes we just give them to the adversary, and the adversary will torture this program to get secrets out of it. So we're asking the question, can a computer program keep a secret even if the adversary captures the entire program? And I want to stress that just like all of you, we're talking about the standard situation. There is no trusted hardware. Everything about the hardware is public and available to the adversary. There's no secret state of the hardware at the beginning. Everything, again, is known to the adversary. There's no interaction between different parties. It's a single ordinary computer. And the program itself is also an ordinary program. It takes ordinary inputs, provides ordinary outputs. It doesn't take encrypted inputs and like encrypted outputs. It's just a standard program. And once again, just running on a single, ordinary, public computer. That is the problem that we're trying to attack. And from a theoretical perspective, right, if we think back in cryptography, this is a long history of looking at secure computation, right? In particular, this concept of secure multi-party computation, pioneered by Yao and Hogarth, McCulley, and Wigderson, and Fedor Goldwasser, Wigderson, and several others. It's been around for a very long time. And actually, we can look at these older concepts in cryptography through the lens of our mind-reading adversary. Right? So if we think about secure multi-party computation, we can think about our program, and these earlier concepts basically took this program and kind of subdivided it up, right, into different parts, and then said that if the adversary can see and tamper with one of these parts of the computation, then we should still have security. Indeed, in the most ambitious form of secure multi-party computation, we could handle all but one of these parts of the brain being entirely controlled by the adversary, and still we could prove security. But again, the fundamental difference between all of this previous work and what we're trying to do is that this idea of spreading out the computation by secret sharing, that's not going to work, right? Because the adversary can actually now look at every part of the computation. And this is what makes our problem so fundamentally different from essentially everything that has come before us in the theoretical realm of cryptography, because again, no part of the computation is hidden, right? Although it is interesting to note that the idea of obfuscation in the theoretical cryptographic community actually dates all the way back to the original paper of Diffie and Hellman, right? Even in that paper, Diffie and Hellman talked about the idea of a one-way compiler as a way of getting public cryptography. So the idea is very, very old, but in terms of having theoretically justifiable kind of ways to attack it, it's remained open for a very long time. Now, if we're talking about this question of protecting secrets within programs, it takes only a moment of reflection to realize that this is not always going to work, right? In the following sense. Suppose I have a program, and it has some secret S in it, but what the program does is a comparison with the secret, right? So it takes an input X, if X is less than S, then it outputs 1, otherwise it outputs 0, right? So again, it only takes a moment to realize that if I give you any obfuscated version of this program, it's hopeless to protect S because a simple binary search will reveal S, right? Just the input-output behavior of the program itself is sufficient to learn the secret S. So in general, for secrecy to be plausible, we would like that the secret is at least unlearnable from the program just with input-output queries to the program, right? And that's why typically we think about cryptographic functionalities as sort of the test case or the application scenario for these kinds of methods, right? Good. So then there is a natural hope here, right? The hope is that can we take a program and somehow convert it into the sort of virtual black box, where despite the fact that I'm giving you the code, it's just going to be only as useful as just being able to talk to it, right? Just only input-output behavior. And by the way, for the purpose of this talk, I will always think about programs as just being, stateless input-output machines. Just think of them as Boolean circuits. All right. So this idea of a virtual black box was put forward in a very old work, joint with Barak, Oldreich, and Pagliacci, and Yang. And we formalized this idea and then quickly ruled it out, right? So we said that it showed that it was impossible to achieve. Now, this is a very often misinterpreted result. So let me quickly tell you what exactly is it that we showed, right? So in that paper, on the one hand, we showed a very strong result, but on the other hand, it's a very contrived result, right? So what did we show? We showed that there are these very contrived programs that I'm going to call self-eating programs, all right? And these very contrived programs exist for which black box obfuscation is not ruled out in some, I rule out some simulation definition, not that kind of fuzzy way. It's explicitly ruled out by means of an attack. Okay? And I think that'll become clear if I show you kind of at a very high level how that works. So our idea was that we created a program, P, that had the following functionality. It had some random secret built in within it. But then what it did was somehow check whether the input to the program was itself a program that was equivalent to itself. Okay? Now, we all know from Rice's theorem this is not actually possible, but we're able to effect it good enough to make the proof work. Okay? So somehow the program checks whether the input is something equivalent to itself, right? And if it ever finds that to be the case, then it just throws up its secret, just happily gives it away, right? Otherwise it outputs 0. So why is the counterexample? Because if I give you only black box access to this program, what is the probability that you'll ever guess an input that's actually equivalent to this program? It's exponentially small, right? Because the secret S is some uniformly distributed secret over, let's say, n bits, right? So it's extremely unlikely that given only black box access to this program, you'll ever be able to figure out the secret. On the other hand, if you give me any obfuscated form of this program, I just feed it to itself, and it notices, oh, this is a program equivalent to me, and just spits out its secret, right? So if this result is strong in the sense that I'm actually showing you a secret recovery attack, right? This actually recovers a secret in polynomial time, and actually quite fast polynomial time, right? On the other hand, it's a very contrived negative result, because who would ever want to obfuscate a self-eating program? I don't know, not me, but I guess it's possible. And indeed, there has been other work in this negative direction since then, but they all, in one way or another, do consider similar pathological scenarios, where basically there's some kind of a self-eating program involved, right? Either indirectly or indirectly. So, what does that mean? I don't know what the word practice means here, but in some kind of practical sense, it's not a totally unreasonable definition to work with at some heuristic level, right? Because the only counterexamples we have are pathological. So how much they say about real life is unclear. But nevertheless, certainly for me as a theoretician, I like to have a definition that, is actually plausible in the general case. So the search kind of continued after this point to find some definition which is going to be at least plausible in the general case. Right? So that led us, in the same paper, actually, to define a seemingly much weaker notion, something we call indistinguishability obfuscation. So what's indistinguishability obfuscation? On the one hand, it's the usual notion of obfuscation. Given a program, it should slow it down by at most a polynomial factor, remember I it should retain equivalence, right? So the output program should be equivalent to the original program. But then the security statement is a quite non-intuitive. Okay, so the security statement says that if you give me two equivalent programs of the same size, okay, so P0 and P1 are completely equivalent, right? For all inputs x, P0 of x equals P1 of x. Okay. If that's the case, then we ask that no polynomial time adversary can distinguish between the obfuscation of P0 and the obfuscation of P1. This is even if the adversary knows and chose by itself those initial two equivalent programs, P0 and P1. Okay, that's the definition. And if you haven't seen it before, if you haven't thought about it much before, it should seem strange to you, right? Because usually when we think about obfuscation, we're talking about hiding some kind of secret. Where is the secret in this definition? It's not so clear, right? I'm saying you give me two completely equivalent programs, and I can't tell which one, which program this obfuscated program came from. So let's reflect on this for a little bit. Obviously, by the way, I want the obfuscator itself to be a polynomial time algorithm. So one way of looking at this is that what we're asking for is a pseudo-canonicalizer. So what do I mean by that? What I mean is that suppose there really was a way to convert every program to some canonical form. Then that would satisfy this definition, right? Because it would take any program, convert it to some canonical form, and any other equivalent program and convert it to the same canonical form, right? So that would, in fact, satisfy this definition. Now, of course, we all know that for polynomial time programs or general Turing machines, you can't hope to find a canonicalizer unless the polynomial hierarchy collapses and all crypto generally goes away. So we don't expect there to be an actual canonicalizer for programs. So instead we're asking for a pseudo-canonicalizer, something that outputs something that's somehow equivalent or indistinguishable from a canonical form. Okay? So that's the idea about what's going on in indistinguishability obfuscation. Let me skip this. So, so this definition we put out back in 2001, there was no impossibility result. If you think about this impossibility I just gave in the last slide, it doesn't apply, right? Because that self-eating program, any program that's equivalent to it, it also throws up its secret, right? So there's nothing to do, essentially. There's no, the negative result is not a negative result for this definition, right? Nevertheless, it was open for a long time to construct it. Another thing I should mention is that this notion of indistinguishability obfuscation has a curious property. If I have a program that is virtual black box obfuscatable, then morally speaking, if I indistinguishability obfuscate it, I will have successfully virtual black box obfuscated it as well. So it's kind of a best possible obfuscation seen in that way. Anyway, the first mathematical construction of this object was given in 2013. This began sort of a gold rush of activity in our field. That was a joint work with two of my former students, Amit and Brent Waters, and then a team at IBM, including Mariana, who's here, and Greg Gentry and Sahai. And it's turned out to be surprisingly useful. This is a little surprising, right? As I just said, it's not obvious what this definition allows you to do, but it turns out that you can leverage it to achieve a lot of interesting applications. So the scale is a watershed moment for cryptography. I'll skip over that. So now there are more than 100 papers, maybe now closer to 200 papers that are built upon I/O in some way. It's been used to resolve long-standing open problems. There's a notion of functional encryption that was solved using I/O for the first time. An old problem called deniable encryption, and a paper that introduced the notion of punctured programming, which turned out to be a very useful technique. It's also been used to introduce new concepts like multi-input functional encryption, I/O for evolving software that changes over time, and way more. I could probably spend the entire workshop talking about my own works in this area, so there's just been a ridiculous number of applications here. And in some sense, what we're seeing is that I/O is such a powerful primitive that you could think of it as kind of the central hub for cryptography. Anything you want to do in crypto, except for efficiency, of course, from a theoretical point of view, you can go via I/O to get to it. Right? All right. So, so for the rest of the talk, I'd like to talk about constructions and security. Again, I won't really have time to go into this at the level of detail that I wish I could. Again, I would probably need the rest of the workshop to do that. So before I get into it, I want to just quickly take a walk down memory lane from the point of view of the theoretical advances in cryptography. And the purpose of this is just to think about sources of hardness in cryptography. Right? So back in the late 70s and the 80s, if we wanted hard problems in cryptography, we would look to things like RSA or factoring or decisional Diffie-Hellman problem, discrete log, those kinds of things. And as a community, we were really successful, right? Starting from these basic sources of hardness, we were able to build public key encryption, multi-party computation, zero-knowledge proofs, and signatures, and much, 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 much more, right? A beautiful garden of cryptography was built there. But then, we started looking at these elliptic curve groups, especially one that supported these bilinear maps. And with this new source of structured hardness, we were able to build other things like attribute-based encryption, identity-based encryption, short signatures. Then more recently, we had this other source of hardness in lattices, right? The learning with errors problem, similar problems for which we built fully homomorphic encryption, and a lot of other beautiful stuff that I haven't illustrated yet. And I see what's happening now with indistinguishability obfuscation is continuing in this trend, right? So we now have these new sources of hardness, something called multilinear map candidates. And from that, we've built obfuscation and this enormous new land of applications for cryptography. This is where we are right now, right? We're investigating this new source of hardness. It's pretty complicated and it's very new, so we want to understand what's going on there. There's still a lot more to be done. Ideally, we would love it if we could take this, this stock here and move its root over to here or over here or all the way over here. That would be great. But what we've seen historically in crypto is that tends not to happen that often, right? Like, for example, for homomorphic encryption, we know how to do it from lattice type of underlying mathematics, but not from factoring, not from elliptic curves. And there's something about the source of hardness that makes that problem difficult. And I think what it shows to us as a community is that we've known since the days of Shannon, right, that we are surrounded by hardness. Almost every problem in this world is hard to solve, right? So there's all the space of hardness out there, and we're only just begun, right? We've only just begun to explore what kind of structured hardness exists and how we can leverage it for cryptography. So we're definitely moving in that direction with this work, and I think there's just an enormous amount of work and structural understanding that we need to build here. All right. So I want to start with a warning. These are purely theoretical results. Known constructions are extremely inefficient. In the next talk, we'll actually hear a little bit about where we are with sort of implementing these things, and it's not nowhere, but it's still at some very initial level. So let's just go straight into it. Let's talk about how this works. All right. So if I'm going to obfuscate a program, the first thing I need is a programming language, right, in which to write my program. So the programming language that we use is something called a matrix branching program. This is a very intuitive programming language. It's one of my favorite languages. Usually when I feel like coding something up at home, I usually write a matrix branching program because it's just so intuitive and obvious. Okay, I'm completely lying to you. That's not the case at all. Matrix branching programs will not seem too straightforward or intuitive to you or to me. I will try to demystify them a little bit. So first of all, what are they? A matrix branching program is given by 2k invertible matrices over some base ring Zn. Okay? And we'll think of these 2K matrices as the program in the following sense. Suppose we have an n-bit input, excuse me. In this example, I'll think of n as being 3. Okay? So I have x1, x2, and x3. The first bit, x1, is going to be my blue input bit. My next bit, x2, will be my red input bit. The last bit will be my green input bit. Okay? And if I want to evaluate my program on some input x, what I do is I use the bits of the input to down select one out of each pair of these matrices, right? So if the first input bit was 1, then I'll select this matrix. The second input bit was 0, I'll select this. So this corresponds to the input 1, 0, 0. And then we just keep repeating. 1, 0, 0, 1, 0, 0, 1, 0, 0, like that. Okay? And to evaluate the program, what we do is just multiply all the matrices. Okay? And the final matrix that we get after this multiplication can be seen as the output of the matrix branching program. Let's ignore what I've written here for a little bit. The main point is that the way we're going to set up these matrix branching programs is that there will always be some entry of the matrix, which will be 0 in the case the output is, let's say, yes, and non-zero if the output is no. Think of it as a Boolean function. So, all right, so what are these programs? Why should we care about them? So just as a little warm-up, let's think about the XOR function and how we might implement that as a matrix branching program. So the idea is that we can associate with the bit 0 the identity matrix, with the bit 1 the anti-identity matrix. And then it just takes a moment's reflection, right, to see that this will work out, right? If you multiply identity by identity or anti-identity by anti-identity, I'll get identity. And otherwise, if I only have one anti-identity, then I'm going to keep that, right? So this is a little cute example to give you some mental anchor. But the real reason we care about matrix branching programs from a theoretical standpoint is that there's a beautiful theorem of Barrington who showed that any log-depth Boolean circuit, so any log-depth Boolean circuit, NC1 circuit, actually has a polynomial-sized matrix branching program. And it turns out, although I won't explain how that works, that we can bootstrap. Once we get obfuscation for log-depth circuits, it's possible to get it for any polynomial size circuit, and indeed for any Turing machine as well. So our goal is to obfuscate this. Let me make one more comment, because again, it may still seem very weird and abstract. Another way to look at these matrix branching programs is as a generalization of finite state machines. Right? If you have a finite state machine, the evolution of that finite state machine is by means of some graph, right? And a graph corresponds to an adjacency matrix. And moving on a graph corresponds to multiplying adjacency matrices, right? That correspond to inputs. So that might be the most intuitive way of thinking about matrix branching programs, is basically corresponding to finite state machines, but then generalized in this algebraic way. All right, yeah.
Sorry, the small n is the index, so n.
Sorry?
Is this n the same n as in MIX? Is the product on there?
The I mod n, that's just the...
It's a different n than the one out there.
No, this n and this n are the same.
It's the same, okay.
And the only thing this I mod n says is that, remember I said we're going to keep repeating, so it goes 1, 0, 0, 1, 0, 0, 1, 0, 0.
You make several rounds. Oh, okay, sorry.
Yeah. And you make several rounds. In general,
okay, yeah.
we will need to go over the input many times.
Oh, okay.
Okay, so it's like a multi-pass finite state machine, right? Okay, good. So this is our notion of a program. To human beings, it's probably already obfuscated, but for actual computing, we need to obfuscate it more. So how are we going to do that? The first step is actually a very, very old idea, beautiful idea due to Killian, which is a kind of randomized encoding of this computation. So what's the idea? Note that we're trying to do a matrix multiplication, right, in order to evaluate this program. So one randomization that we can do here is the following. I can choose random matrices, R1 up to Rk minus 1, remember there are 2K matrices here, to be random invertible matrices. Just as notation, think of R0 and RK being the identity matrix. Okay? And then what I'll do is I will take each matrix here and left multiply by Ri minus 1 and right multiply by Ri inverse. Right? Note that this will maintain the functionality, right? Because these R matrices will cancel out as you do your iterated matrix product. But what's really beautiful about this is that this very, very simple randomization actually allows you to prove the following statement. I can start from the output of this program on some particular input x, just knowing the output, just knowing what the actual final product is. Okay? And from just knowing the output, I can perfectly simulate the joint distribution of all of the matrices that correspond to that particular input. Okay? So this is a theorem from 1989 by Joe Killian, and it's actually extremely easy to prove. So let me actually just prove it to you by example. Okay? Let's think about the case of just two matrices, so just M1 and M2. Right? So in that case, what I'm saying is that I can simulate M1R and R inverse M2 only by knowing M1, M2, the product M1. Right? This is actually easy to see, right? All we need to do is kind of rename things. If I rename R prime as M2 inverse R, remember these are all invertible matrices, right? Then I have R equals M2 R prime, and just rearrange, right? What we see is that M1R is M1 M2 R prime, and R inverse M2 is just R prime inverse. So all I need to know is the product M1 M2, and I can simulate both of these matrices together. Right? And this is the inductive case, right? And if you do induction, you can prove the general statement. So extremely simple idea that gives this really nice property. Right? Okay. So why is that useful? Well, it would be useful if all I had to do was give you the matrices that corresponded to one input. But that's not a very interesting obfuscation, right? If I want to give you an obfuscated program, you'd better be able to run it on more than one input. If you could only run on one input, I would just give you the output, right? Why would I even bother to give you an obfuscated program, right? So it's just the beginning. I now want to figure out a way to use that while still being able to give you all of these matrices in some form. Okay? So it's at this point that we bring a new critical kind of trick in, and this is a kind of encoding. Okay? It's kind of algebraic encoding. This is this M map that I referred to earlier. So what I want to do is encode every entry of each matrix in some way. Okay? Now, what do I want out of my encoding? I want that even though I have an encoded form of my matrix, I should still be able to do iterated matrix product, right? So I need a kind of encoding that on the one hand protects the elements in a way that lets me give out all of the matrices, but on the other hand still allows you to do matrix multiplication. That's sort of the key challenge that we're trying to meet right now. So what's this idea? The idea is what we call multilinear maps, kind of envisioned formally by Bonnet and Silverberg, and then initially the first candidate given by Gard, Gentry, and Levy. And I want to stress this is a very active area of investigation. So understanding how to construct these things is something that we really don't understand completely yet, and we're making progress towards it. I'll come back to this toward a little bit later in the talk. So what's the idea? I'm going to have these rings that correspond to non-empty subsets of some universe 1 through k. And I allow addition at the same level. Think about the set as being like a level. Okay? And on the other hand, I allow multiplication across disjoint levels. So if I have S and I have T and they're disjoint sets, then I can multiply an encoding here with an encoding here, and I jump up to the union of these two levels. that's where I wind up. Why is that? Because I want multilinearity, right? Think of this as being the matrices. The idea is that if I've multiplied in one entry from a matrix, I shouldn't be able to multiply in another entry of that matrix. I want to prevent that because I only want multilinear evaluation, which is all you need for matrix multiplication, right? Matrix multiplication is kind of the prototypical multilinear operation. Okay, and then finally what makes this really non-trivial is the ability to test, once we're at the top level, to know whether I actually have an encoding of 0 or not. Okay. All right, I want to stress to you this point about disjointness, because this is something that is built into this notion, and in fact, in all the evolution that's happened to this notion over the last 3 years, this is something that we really do seem to be able to enforce. Okay, that you can only multiply in these disjoint products. Okay, there are attacks on this model, the way I'm describing it here. Actually next week, my postdoc, Eric Miles, will talk about our work on annihilation attacks, where we show that you can't just pretend you're in this algebraic model. In fact, there are attacks. But we have a new work, which I'll briefly mention at the end, that shows how to incorporate these attacks into the model and still be able to rule out all attacks on the obfuscation scheme. Okay, so what have I done? I've encoded all of the entries of the matrix, right, at these levels, the sort of natural levels. 1 for the first matrix, 2 for the second matrix, so on and so forth. Again, I can do matrix multiplication, right? Because I have disjoint sets. I can multiply across them. I keep unioning them. At the very end, I'll end up at the union of all of these things once again. Good. So the first thought might be, are we already done, right? Could this be a secure obfuscation by applying Killian's randomization, then applying this encoding? So it turns out that the answer is no, and the reason is there's one key obstacle in our path, which is what we call the input mixing attack. Okay? So what is this? Suppose that you're an adversary, and you're mostly nice, right? So you mostly do the right thing. So, you're told that you should multiply these matrices out. So you say, okay, I'll take this matrix, I'll multiply it with this matrix, I'll multiply it with this matrix, right? And note that after these 3 multiplications, you are now committed to your input, right? You're supposed to have the input 1, 0, 0, which means that if you're an honest guy, you're going to multiply this matrix, right? Because that's the matrix you're supposed to multiply next. But of course, you're not an honest guy, right? You're an adversary. So what if you multiply in the wrong matrix, right? Nothing prevents that. I've encoded everything at the same level, so it's just allowed. And indeed, I don't know how to bound the information that can be learned by these kinds of input mixing attacks. And there certainly are explicit counterexamples, examples of programs where these kinds of input mixing attacks would in fact, give up the entire store, kind of reveal the entire secret of the filter. So we definitely need to deal with these input mixing attacks if we want general solutions. So the idea to prevent this is to exploit this set structure, right? I told you that you can only multiply across disjoint sets. I want to exploit that to prevent this kind of input mixing from happening. So my first step is a nothing step. I'm just going to add, I'm going to take my universe from 1 to k and add in new numbers, 1 prime to k prime. Okay? So far I've done nothing. I've just renamed 1 to 1, 1. Okay? But now, remember, I want to prevent input mixing. So what is input mixing? In input mixing, I want to focus on the matrices that correspond to a single input bit, right? And I want to prevent you from mixing these things up. Okay? So the idea is very simple. I'm just going to rotate my second set of indices on the right. So by doing this, what have I done? We can kind of think of these now puzzle pieces, right? If I want to get 1, 1 prime, 4, 4 prime, 7, 7, 7 prime, I want to get all of these numbers. One option is I can multiply everything on the left, and I'll get everything. Or I can multiply everything on the right, and again I'll get everything. But if I ever try to mix these sets together, I'll always end up missing something, right? Because of the way that I've made them straddle each other in this way. So it's a very simple idea. It can be sort of verified in a moment's thought. Again, I illustrate these as these sort of puzzle blocks. If I want to make a rectangle, I can either pick these or I can pick these, but I can't mix them together, right? They just don't fit together. And this is this idea of straddling sets that ends up preventing simply mixing it. And it turns out that I'm now almost done. So if I just add a little bit more randomness, so I have these encoded matrices. They've been Killian randomized in this way, and now I just add one more random scalar in, okay? So this alpha IB is a randomly chosen scalar, distinct for every individual matrix. Okay? Recall that at the end I was just going to be zero testing, so if I multiply everything with a random scalar, it won't change whether something is zero or not. Right? So if I add this, then in fact we can rule out all attacks in that mmap model that I showed you earlier, where the adversary is only allowed to add at the same level, multiply across disjoint levels, and zero test at the top. If this is what we do, we can actually rule out all such attacks. But unfortunately, as I mentioned to you earlier, attacks still exist. Okay, so next week you will hear about annihilation attacks, which are a new high-degree kind of attack that exists over multilinear map constructions that show that even for this construction, there are indeed attacks. You can, in fact, mount an attack that will be able to distinguish between equivalent programs. So, so that's the bad news. But the good news is that sorry, let me tell you a little bit more about the bad news before I go to the good news. These annihilation attacks that you'll hear, that'll be actually tomorrow, I think, is the talk. It gives the first polynomial time attacks on indistinguishability obfuscation over the original GGHM map, and kind of that's the really bad news. But in that same paper, in the paper that you'll hear about tomorrow, we also proposed a weak multilinear map model. So what I mean by that is we take these annihilation attacks, which correspond to these certain kinds of high degree operations that an adversary can do, and we just add them to the model. We say that, hey, you're just allowed to do this. Right? We make the model itself that the adversary is now allowed to do certain kinds of high degree operations. And we can argue informally, but I would need to go into the guts of these mmap candidates to tell you why that this weak mmap model is an intuitive way of capturing the algebraic vulnerabilities that exist in existing multilinear map schemes. Not necessarily lattices vulnerability, those have not really been found. But algebraic vulnerabilities, which is where kind of the action has been, they've all the attacks that have been found in the literature funneled through sort of one weakness, the recovery of an element in a certain ideal that everything goes through. And that is exactly what we capture in this weak mmap model. So then more recently, in a work with Garg, Srivastava, Miles, and Zandri, we actually showed how to construct IO secure with the original mmap scheme. So it turns out, interestingly enough, that we don't need to do that much to make this secure. So remember, we had this construction illustrated here, right? The only thing I need to do to make it secure is the following. I'm going to take my original matrix, MID. Okay? Remember, that's the matrix for the matrix branching program. And I'm just going to embed it block diagonally in a block diagonal matrix, which will have MIB in one part of it, and then a completely random 3 by 3 matrix in another diagonal. That's all. We're just going to embed it with a completely random matrix. I'll have to zero this part out with some vector at the beginning. I'm not getting into that. But that's all I need to do. And it turns out that once I've made this change, now I can actually prove that this scheme is secure even in this weak MMAP model that incorporates all known attacks. And very informally, the reasoning behind that is as follows. It is as follows. In the standard MMAP model, there is this notion that an adversary can go up to degree k, but no higher. Right? There's sort of this ceiling that we place on the adversary that he can evaluate degree k polynomials, but no higher. And the attack that we found is that in fact there are interesting higher degree polynomials that the adversary can build that he can then use to mount some kind of attack. And what we show is that when you are doing that high degree attack, for that attack to be successful, what you need to do is to sort of tame whatever internal randomness exists inside an IO construction. Okay? In the previous construction, that was basically these R matrices and these alphas. Right? That was where the randomness is coming from. And if you find a high degree polynomial that sort of cancels out the randomness in some sense, right? Then that's the problem, and that's how these attacks get formed. But by throwing in this completely random 3 by 3 matrix, it's just a 3 by 3 matrix, what we show is that the values that get created are essentially pseudo-random, or can be seen as being pseudo-random. And therefore, if the adversary is able to produce some high degree polynomial that cancels them out, then he's essentially distinguishing between a pseudorandom function and the output of a pseudorandom function and a completely random function, which we believe to be hard. Right? So that's a very, very rough idea. Again, I would need several hours to explain this in more detail, or at least 1 hour to explain it in more detail. All right. I just want to make one more point, which is that, interestingly enough, also, our original paper, the GHRSW paper, in fact, also had this kind of block diagonal form. All right. But in the original paper, we wanted this ZIV to be a diagonal matrix. So the only change we're really making from our original suggestion, almost, morally speaking, is that now we want it to be a completely random matrix instead of a block, instead of a diagonal random matrix. All right, so with that, I'll like to conclude. So this is incredibly, obfuscation is an incredibly powerful primitive. We're still really at the infancy of this field. I think we are in a stage where we need to explore risky new approaches to kind of go out on the ledge and understand what sources of hardness can be useful to us. One important reason is that efficiency is a ridiculous bottleneck at this point. The current constructions that we have, if you wanted to use it to obfuscate AES, then you would have overheads that easily exceed 2 to the 100. That's a conservative estimate, on the kind of overhead that would be involved. It's only a constant, you don't have to worry about them too much, but it's polynomial time, just unfortunately there's some annoying constants involved. So there's an enormous amount of work that needs to be done to tame this inefficiency. And I think, again, the work that will be there will not just be about playing at the edges, but actually devising entirely new approaches, right? Usually what we found in cryptography is that, there's the initial work that kind of finds the crack in the armor, and then we rip it apart, right? And find all different kinds of ways in. And I expect that to be the case in this as well. And I'll hand it off to the next talk now, who will tell us about where we stand with regard to implementation.
that were 2 to the 128, there would be a possibility here that you could, any program you're obfuscating is going to have a bigger cross in the obfuscation
Right.
than the original.
So again, the only way to interpret the current results is asymptotic, right?
All right.
Pretend we live in a world where we need, 2 to the 100 bits of security, okay? In that case, this would be meaningful, right? In a practical sense. Currently, it is not meaningful in a practical sense, period.
All right.
Right? What it is meaningful is as the first mathematical, theory
Yeah.
that is being formulated to attack this problem.
Yeah, so thanks a lot. Yeah, I can just yell. I was just wondering, when you say this is secure, does that mean it follows that indistinguishability definition these programs had in the beginning?
Yes.
And how does that relate then to extracting the secret from the implementation? Are they
Excellent.
somehow equivalent? Or?
Right. So it's a non-trivial question. I have an hour-long talk prepared on that. I can sit in that right now. Basically, there are techniques. So there are a couple of techniques that have turned out to be very useful. The most useful is something called punctured programming. Okay, so this is something that we introduced in a paper with my student friend Waters, the former student, I should say, now tenured professor. There what we do is we show a technique, kind of a hybrid technique, where you are only using indistinguishability obfuscation, and yet by going through a sequence of hybrid where we kind of rip out a certain part of the program, replace it with something else, and kind of stick it back in, using the security of other primitives like pseudorandom generators and pseudorandom functions, we can actually prove that indistinguishability obfuscation, this weak definition, implies that it is hard to extract some secret. But it is non-trivial. And it's been very successful. There are now more than 100 papers that have used that technique to achieve various kinds of results. But that's sort of the way technically in which you do it. Now, heuristically, I mean, we're too inefficient for heuristically for me to say even those words, but eventually, heuristically, these techniques that we're developing, if they're successful at producing a distinguishability obfuscation, most likely they will be heuristically virtual black box obfuscators as well. So if you think about some far future where this is actually efficient and you want to use it, then you could probably just use it as a virtual black box obfuscator.
Is it easy to turn a circuit into a branching matrix program?
Good, yes. So as I said, that's a two-step process. You start with a log depth circuit, which is a very shallow circuit. And that you can turn pretty easily. I mean, it's a beautiful algebraic proof. It's only like a one-page proof, roughly, of theorem due to Barrington that shows how to convert it into a matrix branching program. There are other ways as well. We have a paper at CCS actually a couple years ago that shows some other natural ways of doing it. So that's not very difficult. But then log depth circuits are very shallow, right? So the way we go from that to general circuits is via fully homomorphic encryption. So fully homomorphic encryption allows you to tackle general depth circuits. And then the decryption circuit for fully homomorphic encryption can be made log depth, and then you can do it that way. Now, that's already a major source of inefficiency because, log depth circuits sound nice, right? But when you convert them to polynomial size branching programs, the polynomial is exponential in that depth, right? Exponential log is only polynomial, so we're fine theoretically. But, these circuits, their depth is at least, let's say, 50, right? That's 2 to the 50 that you already get just from that. So these original recipes, again, our goal was just to plant the flag, to plant the theoretical flag, right? There will be other techniques, and we're already working on them. I mean, I don't expect that number 2 to the 100 to stand for too much longer. I'm still not saying that it'll be practical. I'm just saying that it won't be astronomically ridiculous, right? I like to say the following. Right now, if an alien came from outer space and said, humanity, you have 5 years to implement a paper that was already published on I/O as of August 14th, 2016, and use it to run an obfuscation of AES, and it has to terminate within the next 5 years. Otherwise, I'll blow up your planet. We're gone, right? That's it. The planet is over, right? But I think that if that's the notion, let's say initial notion of like galactic efficiency, like we don't want our planet to get blown up. I think we will be able to solve that problem. You know, after that, we'll see about getting getting closer to practice.
All right. Thank you very much.